Hello students, in our last two classes we have discussed about the group 16 elements. Everybody we know that in group 16 elements from oxygen to polonium these elements are there. So the oxygen, next is the sulfur, next selenium, next tellurium, and last of all that is the polonium. In these five elements, the oxygen and sulfur, this is non-metal, selenium and tellurium, that is metalloids, and last, that is the PO, that is actually the metal. Then we have already discussed about their physical behaviors like melting point, boiling point, density, electronegativity, metallic character. Then little bit we have also discussed about the oxidation states of these elements. Then the various allotropic forms we had already seen. In case of the sulfur, there are so many allotropic forms are there. Next we have already discussed about the hydrides. The main hydride, that is the water, that is H2O, and H2S is also there. So these two hydrides are very important in case of the group 16 elements. Next, the halides. Out of the halides, the main thing, that is the S2X2, Ac2X2, these type of the halides are very important. We have already discussed about their synthetic procedure and few reactions of these halides we have already seen. Next, in case of the oxides of the group 16 elements, the main oxide, that is the SO2, that is the sulfur dioxide and sulfur trioxide, these two are very important in the oxides. Next, another important thing, that is the oxyacids, we have already discussed. So in these oxyacids we had seen that the oxyacids of sulfur, that is very important thing, and we had draw the structure of the oxyacids of sulfur, like sulfurous acid, peroxomonosulfuric acid, Marshall acid, Carros acid, H2S2O5, H2S2O6, oleum, polythionic acid, like that. So now in this class today, that would be our last class of group 16 elements. First of all, we are starting with the ozone. So ozone, that is actually O3. So what are the synthetic procedure are there to synthesize the ozone? Mainly, if we have the oxygen, and if I will keep the oxygen in dry cold state, and if I will apply electrical discharge in this oxygen, then we will get the ozone. And for this reaction, the value of the enthalpy change, that is plus 284.5 kilojoule, that means this reaction, that is endothermic in nature. Okay, so if I have oxygen in dry cold state, and if I will apply electrical discharge into it, then we can get the ozone. The instruments used for the preparation of ozone, that is known as the ozonizers. So mainly two types of ozonizers are there. First one is the Siemens ozonizer, and the second one is the Brody ozonizer. In case of the Siemens ozonizer, we had to pass the electric current through the tin foil, means the SN foils, and in case of the Brody ozonizer, we have to pass the electric current, means the electric discharge, through the copper wax in the dilute H2SO4. So these are the main two differences in case of the ozonizers. So first of all, we are discussing about the Siemens Halsk method. In this method, the electrolysis of acidified water with high density of current using the platinum electrodes, which gives actually 95% ozone and 5% oxygen at the anode. So that is the Siemens method. It is a pale blue pungent smelling gas. So ozone, that is actually pale blue in color and pungent smelling gas. The ozone, that is heavier than air and slightly soluble in water also, and that is highly soluble in acetic acid and the carbon tetrachloride. Again I am repeating, the ozone gas, that is actually pale blue in color and pungent smelling gas, and it is heavier than air and slightly soluble in water. okay, and that is highly soluble in acetic acid and carbon tetrachloride. Thermodynamically, ozone is very unstable and it decomposes to oxygen very easily. How? If I have the ozone, if I have the two molecules of ozone, it will dissociate into three molecules of oxygen, and the value of delta H for this reaction, that is minus 284.5 kilojoule. That means that is the exothermic process. So this process is very easy, and for that reason the ozone is very unstable in thermodynamic approach. So if I will draw the structure of the ozone, so that is the structure of the ozone, you can look that is the structure of the ozone, okay. So the angle between the ozone means the OOO, there are three oxygens are there. So if I will calculate the angle is 116.5 degree, and the bond length, that is the oxygen bond length, there are two oxygen bonds are there, so obviously the two bond length, that is 1.28 and 1.21 angstrom. All the oxygens are there, these are sp2 hybridized, and the bond order, that is 1.5, and the ozone is mainly diamagnetic in nature, that is not paramagnetic in nature. Ozone is mainly diamagnetic in nature. Okay, so these are the physical characteristics of ozone, and we have already discussed about the synthetic method of ozone, and ozone is very unstable, and that is blue in color. These things we have already discussed. Now we are going to the reactions of ozone. If I have lead sulfide, that is PbS, lead sulfide, not T, D, okay. If I have the lead sulfide, and when it reacts with the ozone, it will give white color lead sulfate, okay. So in PbS, the oxidation state of sulfur, that is -2, but in case of the lead sulfate, the oxidation state of the sulfur, that is +6. So here the oxidation is going on, so here the ozone mainly acts as the oxidizing agent, okay. In another reaction, if I have the 2HCl, means if I have the HCl, and when I react that HCl with ozone, we will get chlorine plus water plus oxygen. Here also, in case of the HCl, the oxidation state of the Cl, that is -1, but in case of the Cl2, the oxidation state is 0, so the oxidation number is increasing from left to right. That means the oxidation is going on. So in this reaction also, the ozone is acting as the oxidizing agent. In the next reaction, if I have the potassium iodide, that is Ki, and when that potassium iodide reacts with the water and ozone, it will give the potassium hydroxide along with iodine and oxygen. So in this reaction, if I look the oxidation number of the iodine, in case of the Ki, the oxidation number is -1, but in case of the iodine, the oxidation number is 0. So here also from left to right, we can see that the oxidation number is going to be increased. So the ozone is acting as the oxidizing agent. So now we are going to the next reaction. If I have silver, everybody know that silver, that is shiny white in color, but when it reacts with ozone, then we can look at the Ag2O, that is the silver oxide is formed, and that is actually black in color. And in this reaction also, the ozone is acting as a oxidizing agent. And then after the Ag2 is formed, if I will again pass the ozone gas in excess amount, then the silver oxide reacts with the ozone, and ultimately it will again convert it to silver along with the liberation of the oxygen gas. And the last reaction here, that is you can remember also, that is if I have the stannous chloride, that is SnCl2 in acidic medium, means with HCl, and when it reacts with the ozone, then finally it will give stannic chloride, that is +4 oxidation state of the Sn or tin, and it will form water. So in this reaction, no oxygen is liberating. Okay, so you can remember this reaction. So here also the ozone is acting as a oxidizing agent. So in these reactions we had seen that mainly the ozone is acting as a oxidizing agent, means it helps the oxidation reactions of other elements. When ozone is passed through the mercury, that is very important for your exam, it is when the ozone gas is passed through the mercury, that is the Hg, the tailing effect takes place. The property of lessing luster, meniscus and sticking nature to glass by mercury is called the tailing of mercury. Okay, so when we pass the ozone through the mercury, then the tailing effect takes place. Okay, the property of lessing luster, meniscus and sticking nature to glass by mercury, that is called the tailing of mercury. Actually, in this reaction here, mainly the when the mercury reacts with the ozone, it will give Hg2O plus oxygen. So here the tailed Hg2O, after washing it with water, again it forms the Hg, that is the mercury. So again we can get the mercury, but when the ozone reacts with the mercury, the Hg2O is formed, and that is known as the tailing effect. And finally this reaction is also known as the tailing of mercury. So the tailing of mercury, that actually takes place in presence of the ozone gas. Next, another important point in case of the ozone, that is the ozone bleaches the vegetable color by oxidation. So it also shows the bleaching action. In last cases we had already seen that H2O2, SO2, these type of things are mainly doing the bleaching action. The ozone also, ozone bleaches the vegetable color by the oxidation. So when H2O2 reacts with ozone, it will give water and oxygen. When barium oxide reacts with ozone, it gives barium oxide. When Ag2O, that is the silver oxide, reacts with ozone, it gives silver. So in this case you can observe that ozone is mainly behaving as the reducing agent. So ozone, that is, also acts oxidizing agent as well as the reducing agent. So finally, what are the uses of the ozone? Ozone mainly used for purifying water by destroying the bacteria and virus, improving the air nature in crowded place, oil painting, manufacture of artificial silk and the synthetic transport. So these are the uses of the ozone. And a mixture of ozone and cyanogen, everybody know about the cyanogen. Cyanogen is Cn2, that is C2N2. So that the mixture of the ozone and cyanogen, that is the ozone plus C2N2, this mixture is used as a rocket fuel. Okay, so this is used as the rocket fuel, that is the mixture of the ozone and the cyanogen. These two mixtures are mainly used as the rocket fuel. Okay. So this is all about the ozone. Next we are going to the sodium thiosulfate. So the sodium thiosulfate, that is also very important thing to know. Sodium thiosulfate means Na2S2O3, and when that Na2S2O3 is attached with the 5 molecules of water, then it is known as the hypo solution. Okay, then it is known as the hypo, HYPO, that is hypo. So how can we prepare that? The sodium thiosulfate, how can we prepare? If I have Na2SO3 with the sodium sulfite, Na2SO3, and when it reacts with the sulfur, then if I will boil the mixture, then we can get the Na2S2O3. The other processes are also there. If I have NaOH, and when the NaOH reacts with the sulfur, it will also give the Na2S2O3. Okay. And if I have sodium sulfide, that is Na2S, and that Na2S, when it reacts with the sulfur dioxide gas, it will also give the sodium thiosulfate. Okay, that is Na2S2O3. So these are the main preparatory method. Next, the hypo, that is Na2S2O3.5H2O, that hypo is an efflorescent substance. It can form supersaturated solution. Okay, So if I will hit the sodium thiosulfate dot 5H2O, that is Na2H2O3 at 5H2 or higher at 215 degrees centigrade, then first of all it loses the 5 molecules of water and finally it will form the Na2H2O3. So at 215 degrees centigrade all the 5 water molecules get loosened and finally it will form the Na2H2O3. And if I will increase the temperature to 250 degrees centigrade and above, then the Na2H2O3 or the sodium thiosulfate, it also breaks into Na2H, that is sodium sulfide plus sulfur dioxide plus sulfur. So these are the temperature effect of hypo, and we had already seen the synthetic procedure for the synthesis of sodium thiosulfate or Na2H2O3. Next we are going to the reactions. Suppose I have Na2H2O3, that is the sodium thiosulfate, and when it reacts with the dilute acid, that is when it reacts with the H plus, means the dilute acid, that is dilute HCl or dilute H2O, it will form the SO2, that is the sulfur dioxide, and sulfur and water. Okay. So next we are going to the very important reaction, that is the reaction with the AgNO3, that is reaction with the silver nitrate. Suppose I have Na2H2O3 and that is the dilute solution of the sodium thiosulfate. Okay, that is the dilute solution. So here I had written that is the dilute solution. So when the dilute solution of Na2H2O3 reacts with the AgNO3, it will give Ag2H2O3. Okay, so it will give Ag2H2O3 and that is white in color. It may be yellow, it may be brown, but in maximum cases that is white in color. And when that Ag2H2O3 reacts with the water, then it forms the black color Ag2S. Okay, so you can look the color change in this reaction. First of all, the colorless solution is there, means when the Na2H2O3 and AgNO3 is there, that is the colorless solution, and after the reaction it will form white, then yellow, then brown, and finally if I will add the water it will form black in color. So the color change is very nice in this reaction, and in laboratory if we will perform this test, that is a very spectacular test to observe. Okay. Another reaction is also there. Suppose I have the Na2H2O3, means suppose I have the sodium thiosulfate solution, but the solution is very concentrated. Okay, so in the last case we had already discussed about the dilute solution of the Na2H2O3, and now we are telling about the concentrated solution of the Na2H2O3. So these two reactions are different. When we have the concentrated solution of Na2H2O3 and when it reacts with the silver nitrate, first of all it will form the H2O3. So that reaction is okay, there is no problem, that is similar to the first one. But when the excess amount is there, because we are using the concentrated solution, so when the Ag2H2O3 is formed, again it will react with the Na2H2O3, that is the sodium thiosulfate, and finally it will form the two molecules of NF3AgH2O3 whole 2, and that actually dissolves in the solution. So that actually colorless. So first of all the colorless solution becomes the white, then yellow, then brown. But again if the Na2H2O3 that is in excess amount, then again the colorless solution we can observe due to the formation of NF3AgH2O3 whole 2. So next other reactions are also there. That is, if I have AgBr, that is the silver bromide, and when the silver bromide reacts with the Na2H2O3, means the sodium thiosulfate, it will form sodium argento thiosulfate, that is NF3AgH2O3 whole 2 along with the NaBr. So this reaction is very useful in case of the photography. Okay, so I will discuss it in the next part obviously. So now you just look the reaction part, that is when the silver bromide reacts with the sodium thiosulfate, it forms the sodium argento thiosulfate, that is NF3AgH2O3 whole 2. And the other reactions are also there, like that when Na2S2O3 reacts with the chlorine and water, it forms sodium sulfate along with HCl and sulfur. Moreover, when the sodium thiosulfate reacts with the iodine, it will form Na2S4O6, that is the sodium tetrathionate plus 2 molecules of sodium iodide. So these are the reactions in case of the sodium thiosulfate or the hypo. Next we are going to the uses. The sodium thiosulfate, that is Na2S2O3, that actually used in the photography as a fixing agent due to its complexing ability with AgBr. Okay, so these reactions I had already discussed, that AgBr reacts with Na2S2O3 and it will form the sodium argento thiosulfate. So this thing is also there in uses portion, that is it is used in photography as a fixing agent due to its complexing ability with AgBr in textile industry as anti-clor to remove excess amount of chlorine, is used in bleaching. In lab, hypo is used as iodometric titrating agent for the estimation of copper, that is also used as antiseptic in the medicine. So many uses are there. So this reaction actually tells about the uses of Na2S2O3 in the photography industry. Next, this reaction, that is Na2S2O3 plus I2, that will actually form the sodium tetrathionate. So this reaction actually tells that hypo is used as the iodometric titrating agent in the laboratory, okay, for the estimation of the copper. Next, the other uses are also there, that is it is used as antiseptic in the medicine, in textile industry as anti-clor agent. Okay, so in the textile industry, the Na2S2O3, that is actually used as anti-clor agent to remove the excess amount of chlorine. So for this reaction is very important. You can see this reaction, that Na2S2O3 can react with the Cl2 with the formation of sodium sulfate plus HCl plus sulfur. So that is the main reason that why we are using the Na2S2O3 in the textile industry as anti-clor agent, because it can remove the excess amount of chlorine which is used for the bleaching purpose. Okay, so these are the uses of the hypo or Na2S2O3. And finally we will discuss about few lines or few things about the sulfuric acid, which is also included in the group 16. So the sulfur is there in group 16. So that is H2SO4, that is the oxyacids of sulfur, that is sulfuric acid, everybody will know. So that is also known as the king of chemicals or the oil of vitriol. So how can we prepare the H2SO4? So this thing is also there in your syllabus. So how can we prepare the sulfuric acid? By the contact process. So in this contact process, 96 to 98% acid is obtained. So for this, the few steps are there. So I will discuss few steps here. First of all, we have to burn the sulfur or the sulfide ores in air to get the SO2. Means S plus O2 SO2, or if I have FeS2, that is iron pyrites, and when it reacts with oxygen, it will give F2O3 plus 8 molecules of SO2. Next step, that is the conversion of SO2 to SO3. So we get the SO2 gas. Next we have to convert the SO3. For that we have to react the SO2 gas with oxygen by using the catalyst, and for this reaction the delta value is minus 189 kilojoule. So the reaction is exothermic and the value of delta N, that is minus 1. So to favor the forward process, the high pressure is required, but 2 atmospheric pressure is maintained because the acid resistant towers cannot tolerate high pressure. Next one, that is the low temperature is required, and the optimum temperature is used here, that is the 673 to 723 Kelvin. So these things are giving the idea of use the last atelier principle. So these things are applied here. So minimum temperature means the optimum temperature and optimum pressure we have to give, and the basic assumption of these things, that actually comes from the L'Chatelier principle. Next, when we get the SO3, then the suitable catalyst we have to use which increase the rate of the formation of the SO3. So here we are using the V2O5, that is the vanadium pentoxide catalyst, and the last one, that is the excess amount of oxygen is required to facilitate the reaction. And the last step, that is when we get the SO3 is absorbed in 98% H2SO4 to get the oleum. Okay, so SO3 when we get, then the SO3 it should be absorbed in 98% H2SO4, and finally we get the oleum, that is H2S2O7, and the oleum is diluted with water to get the H2SO4 of desired concentration. So and the last step, the H2S2O7, we have to dissolve the H2S2O7 or the oleum into water, and finally we get the sulfuric acid or the oil of vitriol or the king of chemicals. Okay. So that is mainly the synthetic procedure for the preparation of the H2SO4 by using the contact process, and in this process we can get 96 to 98% of the sulfuric acid. So in our today's class, mainly we have discussed the three important things of the group 16 elements. The first one was the ozone, the methods of heat preparation, and the other physical things are there that actually we have discussed, and the reaction, there is oxidizing agent, it can be used, and it can be used as a reducing agent. These things we have discussed in our class. Then we have discussed the uses of it. Then the sodium thiosulfate, what are the methods to synthesize the sodium thiosulfate or hypo. These things we have discussed. Then the reactions of the sodium thiosulfate, that things we have also discussed, and finally the uses of it. And at last the sulfuric acid, and how can we synthesize the sulfuric acid by the contact process. This is very important for your exam, so that's why I had already discussed about the contact process for the synthesis of the sulfuric acid. So that is all about our group 16. So in our next class I will discuss about the group 17 elements. Okay, thank you.